In this study, we proposed domain-adaptive visual-based global localization method in GNSS-denied environments. GNSS-denied navigation is crucial for maintaining reliable positioning and navigation capabilities in environments where GPS signals are unavailable, degraded, or deliberately disrupted, such as in urban canyons, dense forests, or military operations. Several alternative approaches exist, including terrain reference navigation, magnetic field-based navigation, and vision-based navigation. This work will focus on satellite reference visual navigation, where UAV captured images are matched against stored satellite imagery for localization. Both traditional feature-based approaches like orb sift and learning-based methods like superpoint plus light glue can be applied for this task. However, the matching process is challenged by the issue of domain discrepancy, which arises when UAV imagery and satellite images differ significantly in appearance due to factors such as season, illumination, or viewpoint. The contribution of this work lies in enhancing image feature matching performance under challenging conditions such as varying illumination, dynamic environments, occlusions, and multi-sensor settings. This is achieved through domain adaptation techniques based on the cycle-consistent generative adversarial network. In addition, a marginalized particle filter is integrated with visual inertial odometry to provide a continuous and robust navigation solution, thereby improving resilience in GNSS-denied scenarios. The proposed method consists of three main components. First, VO estimates the general motion of the UAV, though it accumulates drift over time. Second, the image matching module corrects this drift and enables global localization by matching UAV camera images, adapted through CycleGAN with stored satellite maps. The navigation solution is propagated using IMU readings according to the equations below. Both VO and image matching blocks use error state approach for state estimation. For satellite map-based image matching, we employed a marginalized particle filter, a computationally more efficient variant of the standard particle filter. The measurement model for particles at hypothetical positions is formulated as follows. For simplicity, we assume that the camera is gimbaled along the roll and pitch axes, while altitude information is provided by a barometric altimeter. Consequently, the particle's field of view is determined by its X and Y position in the navigation frame, heading relative to north, the zoom level of the satellite map that is proportional to altitude, and the intrinsic dimensions of the camera sensor. The measurement update in the marginalized particle filter relies on particle weights, which are updated using a custom likelihood function. This likelihood is modeled as an exponential function of the number of matched key points between the particle's projected view and the CycleGAN-adapted UAV images. As mentioned earlier, the CycleGAN model is trained to reduce the domain gap between satellite imagery and UAV camera images. For example, UAV images captured during the summer season can be transformed into satellite-like representations, as illustrated. The CycleGAN model is trained using images collected from different domains. Since CycleGAN is an unpaired image-to-image translation method, it does not require capturing the same scene under varying conditions. Also, satellite images were obtained using the Google Earth Pro application. The left image pair illustrates the matching results between raw UAV images and the satellite map, while the right pair shows the results after applying CycleGAN-based domain adaptation. We observed an improvement of approximately 40% in feature matching performance when using domain-adapted images. The algorithm was tested in an offline, on-desk manner. IMU data, camera images, and ground truth states were recorded during flights and later replayed for evaluation. The video presents the test results obtained from real UAV flight data. The leftmost column shows the raw UAV images, followed by the CycleGAN outputs used for image matching. The third column illustrates the views of the most likely particles projected onto the satellite map, while the rightmost column depicts the particle distribution along with the ground truth location. In this test, the proposed method achieved a root mean squared error of 18 meters. The outcome without domain adaptation is illustrated in the figure by the blue trajectory. Due to false feature matches, the algorithm converged to an incorrect location, whereas the domain-adapted version successfully converged to the true position.